Jessica. This is Crash with Biochemistry. Let's begin with a question. How do I get rid of rats in my apartment? And also, how does rat poison work? Today we're going to talk about rat poison, and more specifically anticoagulants. But in order to do that, we first need to talk about the history and discovery of rat poison. The story begins in Midwest USA. During the 1920s, dairy farmers were losing tens of hundreds of cows due to a strange disease that made their cattle bleed to death. Vets soon identified the cause to be a crop in the cattle field called sweet clover that were left to go moldy and then fed to the cows. Despite the increasing number of cows lost to this disease, few dairy farmers could afford alternative feeds and were left helpless. It wasn't until the winter of 1933 that dairy farmer in Wisconsin named Ed Carson found Dr. Carl Paul Link, a biochemist at the University of Wisconsin, in search of help. Intrigued, Dr. Link and his team became determined to find the chemical responsible for the sweet clover disease.
Thankfully, after 7 years of research, they found the culprit. It was a compound named dicumarol. It inhibited blood clotting in a number of animals such as mice and rabbits. One derivative of the compound was so potent in rats that it was developed into a rat poison called warfarin. Warfarin became one of the most popular rodenticides on the market, and by 1954 it was also approved for clinical use in humans under the name Coumadin. 50 years later, many other anticoagulant drugs have been developed, but warfarin still remains one of the most used drugs for rats and people. In fact, warfarin is on the World Health Organization's list of essential medicines. And all of this is thanks to a dairy farmer, a determined biochemist, and some moldy hay, and a load of dead cows.
So how does warfarin kill rats and save humans? Well, first off, warfarin is not dicumarol. So why did we just talk about dicumarol? It's because warfarin is a related chemical derivative of dicumarol that was discovered a few years later. Okay, so this is 4-hydroxycoumarin, and this is dicumarol. Right away you can see that dicumarol is nothing more than two of these just put together. That's why it's called dicumarol. Now here's the structure of warfarin, and again, we see the same 4-hydroxycoumarin in warfarin. In fact, warfarin is just one of the many derivatives of 4-hydroxycoumarin, which all have the same structure and all do the same thing when in the human body. So what do they do in the body, and why is this structure so important for that? Warfarin inhibits the synthesis of blood clotting factors. To understand how this works and see why it can save lives as effectively as it ends them, we first need to examine how blood clotting factors are normally synthesized. With this understanding, we can see how one molecule is both a killer, rat poison, and an essential medicine.
Under normal conditions, the precursors for blood clotting factors 2, 7, 9, and 10, as well as anticoagulant proteins C, S, and Z, are synthesized into their active forms by a reaction involving vitamin K and an enzyme called vitamin K reductase. In the reaction, vitamin K reductase carboxylates a glutamate residue on the blood clotting factor. What this means is that it adds a carboxyl group to the gamma position of a glutamate residue. This reaction makes the blood clotting factor active, and without this reaction, the blood clotting factor is basically useless for blood clotting. Enough about how blood clotting factors work, and back to the reaction with vitamin K. The reaction leads to the formation of something called vitamin K epoxide, along with the active forms of the blood clotting factors. Under normal conditions, an enzyme called vitamin K epoxide reductase takes the vitamin K epoxide that was formed and reverts it back to vitamin K. This way, the body can continue to maintain a constant supply of blood clotting factors in the reaction with vitamin K. This is where warfarin comes in. Warfarin is a competitive inhibitor of vitamin K epoxide reductase, which means that warfarin binds to vitamin K epoxide reductase in place of vitamin K epoxide by resembling the vitamin K epoxide in the reaction. See the similarity warfarin has thanks to the 4-hydroxycoumarin group? With warfarin bound to vitamin K epoxide reductase, the enzyme can't serve its function and can't turn vitamin K epoxide into vitamin K for use in the carboxylation and synthesis of more blood clotting factors. The downstream effect of all this is that there's way less vitamin K available to help form clotting factors. This leads to a lowering of the amount of clotting factors present in the bloodstream, which of course makes the blood less clotty. clot lesser. Less likely to clot. It doesn't clot as easily.
Now we can see how warfarin is so effective both as a rat poison and medicine. As a medicine, warfarin is useful in preventing deep vein thrombosis, heart attack, stroke, and pulmonary embolism. Warfarin is so useful in treating all these conditions because all of them stem from the formation of unwanted blood clots somewhere in the body. Warfarin treats them all the same way, which is by lowering the amount of blood clotting factors present in the bloodstream, which again makes the blood less clottingly. Clot likely? Clot. Alright, less clotting. Anyway, now imagine that warfarin is overprescribed to the patient and the dose is too high. Well, then the patient's blood won't clot as easily, and then they're at risk of excessive bleeding when they get injured. This is exactly how warfarin works as a rat poison. As a poison, warfarin is administered in huge doses, and rats die because the warfarin has lowered the amount of blood clotting factors by such a large degree that the rat's blood does not clot at all, leading them to bleed out to death.
Now that we know how warfarin works in the body, let's synthesize it. The reaction involves adding 4-hydroxycoumarin to 4-phenyl-3-butene-2-one. Added to the solution is anhydrous tetrahydrofuran and acetic acid. We started by taking the mass of the 4-hydroxycoumarin and the 4-phenyl-3-butene-2-one and then added them to a 10 milliliter round bottom flask. We then added the organic solvents, acetic acid and THF. Until all of the solids were dissolved, the solution was heated and mixed with a spin vane. After a half hour of heating and stirring, the final product was completely synthesized, so we purified and isolated the warfarin using column chromatography. The column was filled with cotton and layers of silica gel, and sand served as the stationary phase, and the eluent was dichloromethane. In order to differentiate between the eluent and the warfarin product, a UV light was directed onto a TLC plate as the solvent was administered to it. The eluent appeared clear under the UV light while the warfarin was a strong dark color under the light. This would indicate when to initiate the extraction of the product from the mobile phase. To increase the yield, we concentrated the product using rotary evaporation, which would provide us with our solid product. And finally, we have our solid warfarin.
Thanks for watching this episode of Crash Course Biochemistry. If you were paying attention, you learned that warfarin, or Coumadin, is a derivative of the compound dicoumarol discovered from the sweet clover disease in cows. That anticoagulants are drugs that inhibit the synthesis of blood clotting factors in the body by binding to vitamin K epoxide, reductase, so that the enzyme can't turn vitamin K epoxide back to vitamin K to form clotting factors. That warfarin is effective both as a rat poison and medicine by preventing formation of unwanted blood clots in cardiovascular diseases, and also reducing the amount of blood clotting factors in rats by so much that they die of excessive bleeding. You also learned that we were able to synthesize warfarin in lab by combining 4-hydroxycoumarin with trans-4-phenyl-3-butene-2-one in tetrahydrofluoran and acetic acid solution, followed by column chromatography and vacuum purification.